And I'm very happy to introduce today Sebastian, who is Sebastian is one of our data simulation friends. I think there are many things to say, but I think in 2 words, we were talking with Marco now, which will be the nicest way to brief an introduction to him. And I think what we can say that Sebastian is one of those few names in mathematics that have really helped a lot to shape the discipline of data simulation in the last 10 to 15 years. He has worked on a number of subjects and areas. In particular, has contributed a lot to very nice formulation of the ensemble Kalman filter, particle filter, and in general particle methods. Sebastian is a professor at Potsdam University since 2004, right? Before that, he used to be at Imperial College in London. When I just learned today was when he started to be interested in data simulation. As he got a lot of people telling him this is a subject to work on as a mathematician. So I'm very happy to introduce him. We'll talk today about particle-based algorithms for stochastic optimal control. The format will essentially be the same that you can either wait at the end to get your question, or you can just write your question in the chat, and we will then give it to him. Okay, the floor is yours, Sebastian.
All right. Yeah, thank you. Thank you for the kind introduction. I will definitely come back for more. Anyway, so but in fact, I'm not going to talk about data simulation today. So because can you hear me?
Yes. Okay, maybe you can put the camera.
Maybe I can just
also put the camera if you want.
Oh yeah, we can put the camera on.
If you know how to do it.
It should be somewhere over here.
Yeah. Okay.
So maybe then you can actually see me as well.
Yeah.
Somehow. Okay. Maybe. Oh, I don't know. Now it should not be there.
You can put it down with the little button here.
Oops. Huh?
That one. You can go here.
Okay. Well, let's just move it somewhere. It's not annoying anyone. Okay. Right. I guess we all said. Thanks for coming along, and thanks for joining online. Yeah, as I said, I'm not going to talk about data simulation today, but instead trying to use some of the ideas we developed in data simulation for control problems, which has become my most recent favorite. And so, why is that not moving now? Okay, so I have to click it. Kind of strange. Okay, now it works. Okay. Yeah, so I came across this quote a number of months ago, which is attributed to John von Neumann, who supposedly said at some point in a talk, all processes that are stable we shall predict, all processes that are unstable we shall control. And the story goes that he gave a talk in 1950 in Princeton, and that quote has been recorded from there. And at the time, von Neumann was thinking about numerical weather prediction. So this quote was directly in the context of numerical weather prediction, and von Neumann actually proposed in the talk that we indeed control the weather by sending up airplanes and then dropping some stuff and influencing the weather, which I guess was a pretty bold proposition, but I guess it's still around. Anyway, so I think it's an interesting, still a very interesting and timely perspective. And once you start thinking about control, there are really 2 ways of thinking about this. The one maybe in this audience we're most familiar with, when you think of controlling unstable processes by data, right? So think of your Lorentz 63 model or whatever favorite dynamical system you have in mind. Then there are unstable processes, obviously, and we generally control them by using data to essentially controlling the uncertainties to a certain degree, as much as the data allows us to do. And so, of course, historically, Kalman was maybe the first to really look into this from a mathematical perspective as we like it today, and a Bayesian, even though he looked at minimum variance estimation, but it's basically a Bayesian perspective. And there's this close link to control already there in a traditional sense. But anyway, so that's one way of controlling. But that was not what von Neumann was thinking about in a way. He was really thinking about adding some terms to the system, to the weather system, in his case, that would explicitly control the future evolution of the system. And control theory started around the same time as Kalman's work, and Bellman is one of the big names. And of course, there was always somebody in the Soviet Union doing the same thing. I guess in this case, it's mostly Stratonovich. And so that goes all under the name of stochastic optimal control. And if you don't want to have using a model, so you want to be model free, then it's the world of reinforcement learning. And so there are these two kinds of controls you can think about. And I've been working a lot on data assimilation, as Alberto said. And now I'm sort of moving into this other side of the control. And why is that? So what's new, right? So this is all from the 50s, essentially. And because there's lots of new stuff that happened in between. From my perspective, and of course you in the room here are very familiar with this, is a big step forward was ensemble prediction for numerical weather prediction. Because that is still mind-blowing in a way that in a very high-dimensional system, you can do some sort of uncertainty quantification with a relatively small number of ensemble numbers. Like these days, I think in numerical weather prediction is still 100 or 200 ensemble numbers, which from a statistician's point of view or Monte Carlo perspective is just mind-blowing. And so that, I think, was a very bold step. And then having this technology of ensemble prediction, it didn't take long then for the ensemble Kalman filter to emerge, which is another, if you think about it, this is such an incredible step. I mean, retrospectively, I think it's trivial almost, but to get to this point, it took, remember, Kalman's work was in 1960, so it took almost 40 years to realize that you can implement the Kalman filter in a very clever way for very high-dimensional problems. And and of course, there's been a tremendous amount of follow-up work. And for me, these days, being primarily a mathematician, I started as an electrical engineer. I want to do something useful in my life. Till I then turned into a mathematician. Here we go. The thing that unifies, or what allows you to generalize these ideas, is the picture that the ensemble Kalman filter. The great idea is basically ensemble prediction. You just run an ensemble independently, copies of your model. Now the ensemble Kalman filter, what it does is sort of starts interaction between all these individual forecasts, because you need this information to generate a covariance matrix, which quantifies uncertainty. It also is needed for getting a best estimate, which is ensemble mean. And these two pieces of information then inform the update of each of the ensemble members. But the key thing is these individual forecasts start interacting with each other. So you have an interacting particle system or ensemble system. Particles ensemble is the same thing for me, right? And mathematically, if you would then let your ensemble size go to infinity, which mathematicians like to do, practitioners of course not, you end up with something that's called Minkowski-Vlasov systems. So these are evolution systems that depend on their own distribution. I will give you an example in a second, another example. And the fact that you then have a more general system of evolution equations gives you a tremendous freedom in designing new methods, which of course ultimately you will then implement again as interacting particle systems. And so that's one of the mathematical things that I like, and a lot of my colleagues, at least in mathematics, like as a framework. And the other thing, then you have to design these sort of McKean-Vlasov systems, right? So you have to, there's a huge world out there. You can all sort of games and people interacting games and whatever, use all this sort of framework of McKean-Vlasov systems. But what is key, I think, to devise good algorithms in the context of data assimilation that maybe go a bit beyond the ensemble Kalman filter is this coupling of measure perspective. So basically, coupling of measures, I'm always saying, if you think of Bayes' theorem, I assume you know all Bayes' theorem here in this room, right? You have heard about Bayes. So the Bayes starts from a prior distribution and then goes to the posterior distribution, or the forecast to the analysis for the metrologists. Now you have, but Bayes' theorem tells you these, gives you these two distributions. What Bayes doesn't tell you is to how to go from this one distribution to the other distribution in a sense of the ensemble. I mean, how do you transform one set of samples from a prior into a set of samples from the posterior? The Kalman filter does this in a particular way. You can also do sequential Monte Carlo, where you sample, then you give all particles a weight, how well they match to the data, and then you do resampling. But mathematically, what you're trying to do is to couple this one distribution, the prior with the posterior. Was there a question? No. So all these methods essentially provide a coupling. And once you start thinking from that perspective, that opens the door to use maybe other techniques to couple.
Sorry, Matteo, could you switch off your mic, your micro, please? Thanks.
Okay. And so there's this world of optimal transportation and Schrödinger bridges, which some of you might have heard if you come from machine learning. I had a bit of machine learning background, also become popular in machine learning, and other techniques to couple. This is what I will talk about on Thursday, actually. So this is a bit of a primer for Thursday. So today, I'm not going to talk about this, but I'm going to talk about McKean-Vlasov and type of ideas that come from data assimilation to use in stochastic optimal control. So that's for the general setting. So next for today, how do you use these techniques, or a start off for how to use these ideas in stochastic optimal control? Any questions up to that point? So far, so good. Okay, so this is the description of this of the process I try to control. So it's a diffusion process. X is the state. There's a drift term. There's a control term. U going to be the control. There's a bit of noise, Brownian noise. The thing we try to infer in a way of like to learn is the control term, given some optimality, will be on the next slide, but let's assume it's given for now. And we will learn within a certain class. They will all be feedback control, and theta are the parameters to infer in a way, right? So to learn, but not from data, but from an optimal control perspective. Now, given all this, we know that X will be distributed according to some distribution, which I denote by pi. Depends on time. So the initial condition, let's say it's fixed. So you know where it's starting from. And then you let the diffusion process run. And there's a Fokker-Planck equation, right? So that characterizes the evolution of your density in time, right? So basically, you could throw this away and just work with the Fokker-Planck equation, right? Now, nobody does that, generally speaking, because this, if X is high dimensional, then this is a very high dimensional PDE. Nobody can solve it, right? So instead, what you would do is you run this in a Monte Carlo fashion, so like you do in ensemble prediction. Right? And why are we doing this? Because generally speaking, the density is concentrating in a relatively low dimensional, subspace is not the right word here, but it's concentrating, the probability mass is concentrated on a relatively small fraction of the space, where the particles naturally adapt So it's like a naturally adaptive procedure, whereas when you try to solve the PDE, you would have to solve it everywhere, and it's just very high dimension. It's just huge mess. So it's mainly for computational reason that people solve this SDE now. But it's still informative to look at this PDE here, because you can rewrite. So this is the stuff that comes from the drift. So these two things, that's the drift part, and that's the diffusion part that comes from this here. So this is the corresponding term from the diffusion. Now this term you can rewrite as a drift term, actually, by introducing the log density in its gradient. So if you look at this term and you take this, then you take the gradient of this, you get 1 over pi gradient pi. The 1 over pi cancels with this pi, and then you take another graph, so you get the Laplace. So it's exactly the same thing. But now everything is in divergence form, right? So the gradient, the divergence of something that has a density and then a drift term. So if you then take this, you can again read off an evolution equation, which is the one down here. And so the only thing that has changed, I mean, this and this is still the same. What has changed is that you converted the diffusion part into a drift term, which doesn't involve noise anymore, but involves the distribution of X itself.
But the distribution is related to the noise, no?
No. Well, I mean, it's of course being caused by the noise, which sort of tells you how the things distribute. But this is now completely self-consistent, so you can completely forget about the equation here, right? But the reason why that term is here, of course, you had noise in the original equation, so you had diffusion in the original system. But this is now a completely deterministic system.
This is the tropic force, finally.
Exactly. Yeah. Sure. Yeah. So it's a completely deterministic. So it's now an ordinary differential equation, but it's a McKean-Vlasov system, right? So it's a McKean-Vlasov system because the density appears in the drift term. It's a simplest I mean, it's a classic. I'm not saying this is something new, right? But it's sort of a classic example where you get a McKean-Vlasov system. Now, you could, of course, now argue, well, is that really a great gain? I mean, this is so easy to implement. I mean, we all can draw random numbers. Now here, you have to estimate this distribution. But if you work with an ensemble system anyway, you're already having multiple copies of X, which are supposedly distributed according to pi. And then you can try to estimate the density and put that estimator in. And then the benefit you have from this is that all the particles move completely deterministic. So there's no random wiggling around anymore, right? So they're very smooth trajectories. And if you're lucky, you integrate these equations for long enough. And if this is of gradient type, the particles will actually stop moving at some point. And then you reach stationarity, right? Let's assume this SDE has a stationary distribution if you run it for long enough, right? So there's a stationary solution here which makes the time dependence 0, right? So then this system down here, under some additional assumptions, we can construct examples where particles will still run in circles, for example, or something. But in particular, if this is of gradient type, then the particles will sit there, and then you reach equilibrium. Yep.
In this case, you have an equilibrium which is in tail balance because you are vanishing the current.
Yes.
In the Stochastic equation, you are not sure that you get the tail balance equilibrium.
Yeah. So you would have to have a condition where the flux disappears.
Condition of the twist.
Right. So, but like if it's gradient type, then we know you have the Boltzmann distribution, then everything is good, right? Then you have a solution for this. But I totally agree in general, of course, it's not necessarily the case, right? That the flux disappears. These are nice things. Now, of course, you have to be careful, right? So this has non-differentiable solutions. This has smooth solutions. So path-wise, they don't agree, right? But in distribution, they agree. Right? Now, in data assimilation, we're often only interested in sort of distributions. Then this is good enough. If you really want to know the time trajectory and you want to have it precisely, then individually, then first you can't make this transition. Okay, but we will play this game. And in this context here, I also introduced it for you so that you see an easy example where McKean-Vlasov appears. Yeah.
What about the regularity of the coefficient? I mean, in particular of the control U. What's the regularity we are assuming?
So I don't know. You mean U being differentiable as a function of X? Well, here I mean, okay. So I assume for this to make sense, you have to assume some sort of Lipschitz continuity results to have existence of solutions to begin with. For here, I definitely will assume that these functions are differentiable and nice. But I mean, here at this point, at least, this is just a given, right? So here you can give any control, and I just did this the question that you're asking arises later when I say, okay, I want this to minimize some sort of cost, and then the questions of regularity arise, etc. Right? Okay. So, and that indeed is the next step. So for now, we just took U as given. Now, a typical control scenario is that you have some quantities of interest, which I will denote by psi, which depend on the state of the system. And you want to sort of control these quantities of interest. And let's, for simplicity for this talk, assume that you try to control them. They take some reference value, right? It's an easy particular scenario of control theory. So then you can also set up various scenarios on what kind of cost you want to associate with this. So here's just the L2 cost. And then the cost function you want to infer or minimize, sorry, is the average cost over infinite time. So you end up with we penalize the control. That's the control penalizing term. Again, just the L2 norm. Then the cost, which comes from what you actually want to control. And you look at the infinite time optimal control column. So T goes to infinity, and you average, and you also take expectation with respect to the distribution. So you, whenever I have an expectation here, then it means I take expectation with respect to pi t, which I had on the previous slide, right? And then you want to minimize that over. Now here I already parameterized the class of controls. So you have a set of parameters, theta, which you are allowed to vary. So these are the thetas here. And you have to, whatever function approximations you want to use. And so you want to minimize that. So in the principle, it's a very simple task to do, mathematically speaking. But there's little catches. So first of all, let's assume that the diffusion process we're looking at is ergodic. So it has an invariant measure, unique invariant measure. And why are we doing this? I mean, the simple reason is because we want to get rid of the dependence on X naught. So, this whole complicated expression can be boiled down to taking expectation with respect to that invariant measure. Right? So this is still the same cost as we had before, under the assumption that there is such an invariant measure. So now things have simplified even further. So now we have a very nice expression here that we want to minimize with respect to theta. For notational convenience, I will also introduce now sort of a complete sort of cost function, which includes the previous cost with respect to the reference value and the cost with respect to the cost to the control. So so I will just use this shorthand. And so what we now left with is we have to we want to minimize. It's useful to have a gradient, right? And so we have to find the gradient of this cost function with respect to theta. Yeah. And that's partially easy and partially difficult. The easy part is if you do sort of differentiation with respect to the cost function, that's easy, right? Because that boils down to differentiating this expression with respect to theta. You can do that. The complicated thing is the dependence of the invariant distribution with respect to theta. Right? That's highly non-trivial, except for very simple cases. Also, just for notational, I mean, I hope that's clear what I mean by this here. So what in the bracket here, that's expectation of this expression with respect to that distribution, right? So what's written here really is an integral of this expression with respect to that density. So that's the short end, right? So right. So how do we find this? Now, if you go into the control literature, of course, there's a solution. It's a very elegant. Again, it's probably goes back to the 50s or 60s again, this sort of thing. So you look at the generator that comes with your controlled diffusion process. So think again of the SDE I had at the very beginning. That's the diffusion process. If you have a diffusion process, there's a generator. There's an operator that acts on functions and allows you to compute expectation values again on the level of PDE, so to speak, right? So it's a dual picture of the Fokker-Planck equation I had before, right? So the Fokker-Planck equation is also a linear PDE, and it has sort of an operator, and in fact, that operator is a dual of that operator, which is called a generator. Okay, and it takes this particular form. So again, this part comes from the diffusion process, and that comes from the drift. Okay, now with this generator, you can associate the stationary Hamilton-Jacobi-Bellman equation, where you look for functions y of x, which will depend on theta. So theta is for now fixed, right? Let's assume you've chosen a set of thetas. So for fixed theta, you have this linear partial differential equation, where the cost appears again, the total cost, and its expectation value. You need to take that term off because otherwise this operator has no solution. Anyway, so this is the Bellman Hamilton-Jacobi-Bellman equation, and let's say we know the solution of that. We can solve this equation, which again is as complicated as solving the Fokker-Planck equation, which I had at the first slide, the first mathematical slide. So it's a mathematical construction. But if we have that, then the following nice trick applies. If you want to now compute the gradient of this cost functional, then you use this identity. So you replace this by these two terms, right? You put those here. Then you can still take expectation there on both sides, right? This here is already, this is just the vector in theta, so it doesn't depend on x anymore. So if you take expectation here, nothing will change. That just remains the same. And here you get the expectation on that side. So that's what's written here, right? You're taking expectation now on both sides. Here it just disappears. Now you do your integration by parts, then you see that the derivative of the of theta with respect to y of theta vanishes because this operator, the dual, is the one that appears in the Fokker-Planck equation. Now p theta is invariant, so this has to be 0, right? Because if that's not 0, then it would not be an invariant measure under the Fokker-Planck equation. So you don't need the gradient. I mean, so that means that down here, the gradient with respect to y theta, or of y with respect to theta, disappears, because basically you pull the gradient over here, then the L is here, then you do integration by parts, you shift it over to the pi, and that gives you the dual operator. That's where this then applies, which makes it 0, right? So you're left with this, and so you need the gradient of the cost function with respect to theta, and you need the gradient of your generator with respect to theta. Both of these objects are easy to compute, because if you look here, it boils down again. If you take the gradient with respect to theta here, it just is a gradient with respect to u, and then theta. So all these things can be now computed. And then, of course, you have to compute the expectation values. Okay, fine. Somehow we assume we have the density. So that's a very well-known trick also in machine learning and reinforcement learning. Time differencing, all these methods rely on this sort of trick. And once you have the gradient, then you can do gradient descent and find the best theta.
But of course, here you need the assumption of a glotticity, otherwise you will not be able to make that separation of dependence on theta.
Yes, I mean, yes. I mean, here we rely heavily on, yes, so that this is satisfied, right? Satisfied.
So in case of theta being, the system is not stationary, for instance, of p pi, depending on theta in a more complex way, that will be.
Well, it's not the end. I mean,
no, it's not, no.
I said it this way so to make life easy for you actually, and also for me for this talk actually. But there are variants. I mean, basically, if it's non-stationary or if you look at optimal control problems over finite time, then you have to deal with the time-dependent variant of this, right? But it's it just gets more technical. But the ideas are still the same, that the value function has to satisfy basically a Hamilton-Jacobi-Bellman equation, which is of this type, where the generator of the forward process appears. And it's a PDE, right? So by the Jacobi, by the way, I have to put this in here, was born in Potsdam. Potsdam wasn't a university then, so you had to go to Königsberg. Embarrassingly enough, there's still no street named after Jacobi in Potsdam. So there have been attempts, but for some reason unsuccessful so far. But as was Humboldt. Humboldt was also, I mean, one of the brothers was born in Potsdam actually. One of the Humboldt brothers was. But anyway, we're not quite as old as Bologna as a university. We're still under 50 actually. So our rector is very proud of us because we under the 50s, we actually pretty good in the rankings, right? But soon we're gonna slip out of the under 50s, so we're gonna lose the bonus of being young, and then we have to compete with the established big boys. Anyway, so here, yeah. So I guess I can mostly skip this. I mean, this is just an illustration. If it's a linear, if you make this linear ansatz, you know, you can, yeah, I don't think I have to do much here. Now comes sort of the going in the direction how to solve this issue, right? So basically, if you're happy solving PDEs, and if you can do this in high dimensions, you can leave the room now. Because then the rest for you is of no interest in a way. But most people struggle with solving high-dimensional PDEs. So you don't want to solve the Fokker-Planck equation. You want to use particle methods. And so basically what I'm trying to show you that there might be a way of using also particle methods to do this here and to compute the gradient.
How many dimensions you need? Over 3.
Yes, let's say, right? I mean, definitely more than 3. I mean, I think it's in 3 dimensions. I mean, in 2 dimensions, we can easily do it with MATLAB. In 3 dimensions, but yeah, let's talk, say 10, right? But in weather prediction, you would talk about a few millions, right? And we do data assimilation in a few million degrees of freedom with a few tricks, right? But yeah, let's stick to more than 3. I'm glad nobody's leaving. Otherwise, I would have just increased the number and would say, at what point are you willing to stay here? Anyway, so this is another standard trick, right? So you do the Kohl-Hopf transformation. So instead of solving for y, you're introducing the function v, which is just e to the -1. Now, okay, so that's often done in optimal control to linearize a problem. So you replace a nonlinear problem by a linear one. In our case, actually, it does the opposite, right? And we already had a simple linear PDE. Now we made it nonlinear. And furthermore, this transformation leads to an additional term. You just do the differentiation, and so you get this another term, which we encountered already, right? At the very beginning, when I had the Fokker-Planck equation, we suddenly had this grad log P term. Now we have a grad log V term there, but it's sort of the same sort of thing. And so we're gonna play with this now. And there are 2 things we're gonna do now. So first of all, when you try to solve a stationary problem, then often you do a time embedding, right? So you say, okay, I take the stationary solution as a fixed point of a time-dependent problem. So time here is now sort of an artificial time for now. And so we get a time-dependent Hamilton-Jacobi-Bellman equation in V, but of course we're interested when this is 0, when it's stationary. Okay, that's not a big deal. Now the second thing is more important. So we assume under suitable conditions, I mean, that these are actually satisfies if the process is ergodic, that this will also converge, right? So so here's the key idea. We're gonna introduce a second density. So we have our invariant distribution of the forward SDE process under a given control. And now we're putting our Bayesian head on it, pseudo Bayesian, and saying this is our prior distribution. And this object here, which is the member of the form here, we take sort of as a likelihood, time-dependent likelihood, because this is evolving in time. Of course, eventually this reaches stationary, so that then becomes a stationary likelihood function. And you do Bayes to define a second distribution. All right, so this is a head. So in other words, what we're trying to do, we're gonna try to translate this column, which is a PDE, which, you know, one can argue, and there's a very clever numerical methods to solve it, but there are no particle methods for this really. So we're trying to convert this into an evolution equation for a density, and then having particle methods available. Okay, so then you crank away, do your arithmetic, and you find the evolution equation for the p hat, which is a bit unpleasant. So first of all, so the dual of the generator of the process appears again, which is sort of okay, because that's sort of the diffusion process we started with. So that's we know how to sort of represent, except there's a minus sign in front of it. So the thing is running backward in time. Now, running things backward in time with the diffusion process, a bit shaky, but anyway. So then there's this term coming in, which is grad log G term. And then there's further terms coming in the red team. So now the blue terms, whether you like them or not, they easily translate into particles, right? Because they are of diffusion type, even though the sign is not right, but okay. And this is also easily, I mean, this is already of flux form. So, you know, you have this term as another sort of drift in the SDE, and then you have this bit, the red bit. Now, if you come from data assimilation, then this is not so scary. Because time continuous data assimilation has exactly that term, where this would be data driven. In fact, it would be the C would be the grad log, the negative log likelihood, right? That appears from data assimilation, continuous time data assimilation, right? So anyway, so this, if you know time continuous data assimilation, that's actually something we can cope with. And this, well, if you come from particle systems, it's also not hard. So, so here is our, you can then find the corresponding McKean-Vlasov system, again for fixed theta. And so you get the original drift with a minus, the control term with a minus, you get from the diffusion part here and from this. Remember, this V is actually the grad log V is the grad log difference between the posterior and the prior density, as I called it. And so these things are appearing here. So this is the prior density, that's the posterior time-dependent density, quotation mark. And then you get another term from this, which is like the control you get from data assimilation, quotation mark again, because this is now not, this is not a data-driven term, but it's a term that comes from the control. And so the G hat has to satisfy this elliptic equation down there. Again, if you're familiar with time continuous data assimilation, that's something that you see. Okay, so that looks horrendously complicated, doesn't it? Anyone agrees? But I mean, for now, we've sort of achieved, at least we now we can solve the original diffusion process. We can solve, I mean, if we manage to put this onto a computer, we can solve this in a particle way. So we have two particle systems that evolve forward in time, and somehow both have a distribution attached to them. The difference of the two tell us something about the gradient, how to improve the theta. Okay, so here comes the even more scary slide, but it's the overall picture that you can put onto a computer. This is the forward evolution process. Again, I replaced diffusion by the grad log density term because we will have to do this estimation anyway. This is the backward process, no, it's not the backward process. It's the second process I just introduced on the previous slide, which is very much like this here, except that the signs have changed here. You have an additional driving term, and then you have another sort of these grad log terms appearing. And then finally, the third equation tells you how to upgrade the theta. And that requires a density from this process. And so you have now a time continuous system in time, which hopefully as time progresses will give you the optimal choice of parameters and optimize the whole thing. So there are various colors here. So the blue things are all grad log density terms, and so we have to estimate those. So that's still open how to do this, and I will tell you two ways to do it in the next slides. And then there's this purple term here, that comes with solving this problem, which is also doesn't look easy. So I will again tell you one or another way of doing that. And the red term is, well, that's the approximation to the gradient of the cost function. There's actually no further real complication here. I mean, this we already estimated in the other blue terms, and density we can approximate again empirically by running this via a particle method. Yeah. Yeah. Okay, so let me just quickly run through this elliptic equation, right? So now, if you want to solve this approximately, you can make a Gaussian approximation on pi. That's what the Ensemble-Kalman filter does, for example. And then you do exactly the sort of machinery of Ensemble-Kalman filtering. So that you approximate the desired drift term G, which has to apply in this equation, by computing covariances between x and psi, this psi which is in the cost function somehow, and then here you have psi minus this expected value. So summary, I don't have much time. Basically, you're using the Ensemble-Kalman filter at that point to solve this problem down here, or to approximate this problem down here, right? And you can use any ensemble method you like. Then there's another neat trick, which I don't have time to now, how to approximate these terms. And just as a keyword, if you're familiar with this, we're gonna estimate the grad log density terms using diffusion maps. I don't have time to say much more about it, but it's diffusion maps have been widely used in machine learning and elsewhere for dimensional reduction, but they can also be used as a tool to grad log density estimation. And so then basically you put everything together and you have a method. And the thing is, I mean, this is a very simple example. So I looked at the double well diffusion process where the saddle point is at 0, which is unstable. And so you want to stabilize this 0 point. And you apply, I mean, this is of course a very simple example. So you apply this technique with 3 particles here in this case. I mean, you run each of these, did I say somewhere here? No, I don't say here. I think 3 or 5 particles used in the simulation. I mean, very small, I mean, it's also one-dimensional, but it's still one-dimensional PDEs you're trying to solve with basically 5 particles. And oh no, wait a minute. So here the number is actually here. Yeah. So I use the reference at 100, 10, and 3 particles. But 3 particles also works. I mean, you see it's maybe not optimal, but it's very close. So it looks reasonably robust. And the other example we ran was an inverted pendulum, which is a bit harder when you try to get the pendulum to move up to the upwards position and then to stabilize it there. So you move it really from the stable downward position and then you drive it up by a control term to the upper position. That's actually a non-stationary control problem where you have a finite time constraint. So that is an example where you're not talking about invariant distribution. So you really want to, you have a finite time control problem, but basically using the same machinery. And so and you want to do it over 1 unit of time. Again, I don't really have the time to go into this, but the most important point, again, that we managed to do this in a rather, again, like 5 or 8 particles. You see, this is the lower position, this is upper position. So the control term drives it smoothly from one to another. The velocity is a bit more kinky. I mean, you first accelerate and then decelerate because you want to stop at the top position. We also used linear control laws here, time-dependent linear control laws as a parameterization. And that's it. All right. So now, what have we done? We sort of build a bridge between some of the methods that we're using in data simulation, converting them into control. The idea basically is to not work with Hamilton-Jacobi-Bellman equations, but trying to get it into the Fokker-Planck picture, for which we then can use particle methods. We need grad log density estimators. So we used, and we need to approximately solve Poisson equations, but we use techniques that have been around. Now, we're definitely not gonna, with these techniques, we're probably not gonna be able to scale it up to 1,000,000 degrees of freedom. We'll have to use tricks like localization, et cetera, et cetera. And then if you really want to get tough, you really want to have if you do your PhD and you don't have a topic yet, and you have lots of time, more than 4 years, then I recommend really trying to solve both. I mean, the data assimilation problem and the optimal control problem simultaneously, which is called partially observed Markov decision problems, which are, I think, the toughest problem out there altogether, because you then the control laws are no longer state dependent; they depend actually on distributions, which is a completely different world. Okay, there are a few papers here. I will leave them up, and thank you for your attention. Yep, we'll do.
Okay, let's take let's take some questions there. Let me first ask on the audience online if you have questions. Maybe if either you speak out, you switch off on your microphone and you speak out, or you write them in the chat, and then I will report it to Sebastian here. Otherwise, we can also take picture from the room if there are some. Yeah, please. So just 1 second. Let me take your microphone closer. So I will take you down. I'm happy to do that. Just speak here.
So I'm working different topics like traffic, but in any way we have problem control of traffic, and your control technique is something that acts local control the system everywhere. So in some sense, if you want to also not only minimize the energy of a control, but also you want to have a local control in order to get a global solution that optimizes something. That can be applied or not?
I'm not sure. Are you referring to the model predictive control where you really compute the control wherever you are?
Sometimes you want to have you have a system which is large, but you say, okay, I have only a few points or in the sum of points, but limited, where you can control the things, and if you want to be able to understand if your local control can change the situation, the distribution of your system in a global way.
Well, I mean, I would say you can see what it globally does, because basically you would simulate the system on the whole scale. I'm not sure if you would still be able to.
Means that it is everywhere.
Yes, that's the X would be everywhere, but you can, I mean, well, I mean, let's say in data assimilation, how we do data assimilation is also we basically adjust locally the fields, right? The data should also only locally affect the state of your model. It shouldn't affect it globally. And that's actually key to the success that the data assimilation algorithms work, that you do this local adaptation. Now, I would imagine I haven't talked about it, but I mean, I would definitely, if we want to scale it up to high dimensions, you would like to do something similar, that you devise control laws that act locally, and then see how well this behaves globally as an approximation. But this is something I haven't talked about, but I think if this should be scaling up to high dimension, then this would be probably the way to go, very much like we've done this in data assimilation, where we actually have the same issues. I mean, does it really guarantee you stability if you locally adjust the fields from the data? But intuitively, it makes a lot of sense. And there are some results actually on proving for data assimilation that it actually works. Of course, as all mathematical results, you make ridiculous strong assumptions, so which never apply in practice. But I would definitely do this in this context as well. Yeah.
Other question from the room or from the virtual room? Any curiosity? Maybe I have one. Could you come back a bit, 2 slides, on the first example that you were showing, the one, I just want to understand a bit better if I can interpret the theory from the numerical result. Yes, here. So, I'm giving a question. So, what are we looking at there?
Okay, sorry, I mean, I was running a bit of time.
Yeah, I know.
So here down there is indeed time. Yeah, so I initialize the system with theta equal to 0, let's say, with some choice of theta. And that's clearly non-optimal. And then I also don't assume that my particles are in equilibrium. So I really run these 3 systems of ODEs in parallel. And that's what time is here. And then what
So the initial condition is also different from the 3 particle.
so the initial conditions are not the equilibrium distributions. So I mean, it's a double well potential. So some particles on this side and some particles are here. That's how I start in a way. And then I switch on the control and I time continuously learn the control. And so what you see here, that it quickly equilibrates. And again, you see, these are very, I mean, except for this funny stuff, M equals 3, where I guess it's just a very bad approximation initially to the gradient, but it sort of captures it, you know, it sort of recovers. But you see these curves are all very smooth. And that's because I don't have noise in the system, right? So even I solve a diffusion problem, I do these estimations and replace this movement by these gradlock terms. And so that's why it's calibrating so nicely. If you would use noise, then it would still wobble around. Right? And you would have to use lots of particles to then see that the mean converges to something. Right, so yeah. And here, these are the real trajectories with noise, right? So these are the real trajectories with the control, but with diffusion process. So I mean, the real process you're trying to control, right? So that's why this is wiggly. If I would have taken out the noise here as well, then it would again probably be a straight line, just 0. But we want to control the real process, not some computational model of it, which changes the problem. Yeah.
I have another question. Can I? Of course, if there is anyone in the room or in the virtual room, just raise the hands, both the real hand and the virtual hand. You have mentioned connection with the diffusion map. Could you elaborate a bit more on this?
Yeah. So
because it's the microphone.
yeah. So if you have this gradlock temperature term, now again we look at the generator of a process that has this as a density, as an invariant. So I don't know how much you're familiar with. You have Langevin processes. It's the x dot equal gradient log the density plus noise, and that has the density pi as an invariant density. So this is now the generator for this process, not of the original process, but the Langevin process that has this as an invariant density. Now, then if you just have this, that the gradlock density term comes out of this identity in the limit epsilon to 0. So you take the exponential, the semigroup of this generator, and have an artificial epsilon there, which you set to a small number numerically. Now, if this is a small number, then to approximate the semigroup, there is the diffusion map. If you have samples from the distribution, so we assume we have samples from P, but we don't have P itself. We only have samples. Then you can still approximate that term very well using diffusion maps. How this works is a different story, but it's a well-known technique. So then you basically approximate this by the diffusion map approximation, and you get basically you replacing so you apply the diffusion map to the identity minus identity that you can also do with the particles, and so this is what gives you the approximation to the gradlock density term. That's how it comes about. It's actually something, if you're a bit into machine learning and generative modeling, and if you heard about score generative diffusion models. Who has heard about score generative diffusion models in this room? Or diffusion generative models? I mean, SDEs, yeah. You see everywhere there are the scores, right? What is the score? This is the gradlock density term. That's the score. So that appears everywhere. And so so you don't have to be afraid of it. I mean, machine learning people doing this in very high dimensions now, right? I mean, in principle. So and yeah,
it is also
exactly. Yeah, sure. I mean, but computationally, people now sort of get a handle on how to do these things, and it appears in score generative models, which work in very high dimensions because you basically generating images. Yeah, and again, the idea is there that you actually don't have the density; you only have samples from the density, right? I mean, your images you're trying to generate more samples from. Yeah.
Okay, if there are no more questions, no one from the virtual room spoke out. Let's thank Sebastian again, and that has been, as I say, a series of webinar for SASIP. There will be other ones. We ranges from different topics, and so let's thank Sebastian again. And let me remind to those of you in the room that Sebastian is going to be here until the end of the week and is going to give a second seminar. This is a bit more on data simulation side, and it will happen on Thursday at 4 p.m. in room A in the Viernerio building. Okay, thank you. Ciao, ciao.
Thank you.
Thank you.
Yeah, I mean, if you wanted to talk whatever topic.